Okay, good morning, everyone. Welcome to the ICTS Math Physics Seminar. Our speaker today is David Sauzin, and he's going to talk about Resurgence and partial theta series. Over to you, David.
Thank you, Pranav, and thank again the ICTS for the wonderful hospitality. So I'm going to talk about this work. It's a joint work with Li Han, Young Li, and Shamsung Sun. And so there is a preprint available on HAL. This is hyperarticles online. It's a French thing, alternative to archive. So maybe it's an allusion to the mad computer at the end of Stanley Kubrick's movie Space Odyssey, you know, the mad computer, HAL. Anyway, so here is the reference, 03502404. Since I'm going to give this Blackboard talk, maybe I cannot give all the technicalities, and I don't want to overwhelm you with too technical details, but you can refer to the preprint to have a look at the details. So the title of the preprint and of the talk is Resurgence and partial theta series. So partial theta series, what we mean is a series of the form theta of tau equal to sum over all positive integers of, let's say, n power nu f of n exponential I pi n square tau over m. So you see in theta, you always have a sum of exponentials with the n square, but here it's only for positive integers. This is why it's a partial theta series. It's not a full theta series. So what are the notations? Tau is the variable, n is the summation index, and m is just a parameter, it's just a scaling, it's a convention, but we will choose a sequence of coefficients periodic with period m. So here in practice for us, f will be m periodic on integers. So m is a positive integer, and nu is an exponent here. Nu is 0 or 1 or higher integer. And so, of course, you see where the series converge. The modulus of the exponential is the exponential of the real part, which is minus n squared pi over m imaginary of tau. So this will be very convergent thanks to the n squared, provided imaginary of tau is positive. So we are working here in the Poincaré half plane. So tau is here, the Poincaré half plane H. So this would be 0. And you see that we have a sum of exponentials, and of course, this is a periodic function of tau of period 2m in general. So this is 2m periodic in general. And this is the Fourier expansion. So in the literature, very often they use Q to be exponential 2 pi I tau. So these are powers of Q. So it's a Q series if you use the Q variable, or you can view it as a Fourier series, but only positive modes, which means that the function is defined in the upper half plane and tends to 0 and is exponentially small at infinity. So when you go to infinity, it becomes exponentially small with respect to imaginary of tau, of course. And we are interested in the boundary behavior near the real axis, near the rationals. This is what we want to know. Pick alpha here, a rational. And we wonder what happens when you go, let's say, toward alpha, maybe radially. I mean, I say radially if I follow a vertical, because this would correspond in the Q variable, this would correspond to going along a ray. So this is exponential 2 pi I alpha. Or non-tangentially, more generally, non-tangentially in a sector like that. So the variable is going toward that point. What happens to the function? This is a classical question. You can view that as a chapter in analysis. We are dealing with a class of functions. And so we will define QF. You see, I mean, we will vary the function. So, I mean, the full notation here, it depends on U and F and M. And so let me define QF to be a set of alphas so that the limit exists, simply the non-tangential limit. So let me use this notation. Tau tends to alpha non-tangentially, and this exists. So if it exists, we give it a name. It's theta nt of alpha, the limit value at alpha, and this will define the function theta nt on this set QF, and also at infinity, by the way. At infinity, the value is 0. So this is a subset of the boundary of the Poincaré half-plane. This is what we are interested in. So the question is, what can we say about this limit function, about the asymptotic behavior? How do we approach the limit? Is there, behind the limit, is there an asymptotic expansion? Is it resurgent? Let me already announce you one of the results, I mean, which is very well known probably. I must say that many things in this preprint are not really new. What is new maybe is the resurgence viewpoint, giving a unifying framework for various phenomena which have been observed in the literature. So let me announce one of the results. Is 0 a point where the limit exists? Yes, if and only if the mean value of f is 0. The mean value of this periodic function f. That's something we will prove. And then immediately you see that you have a description of the whole set simply by the following trick. What happens when you shift variable tau by alpha? I mean, you start with function f, which has a period m, and you shift. So, of course, you are shifting here. You have, well, nu, f of n, and then, well, you have something, let me call it lambda alpha over m n exponential. So lambda, this is a notation, lambda beta of n is exponential I pi n square beta for beta rational. And you see when tau plus alpha, I have alpha over m coming out, and then the usual exponential. And now the point is that this is periodic as a function of n, with a period depending on the denominator of beta. So this whole thing now is periodic, with a period depending on least common multiple of m and the period of lambda to the lambda beta. So this is another partial theta series at tau using, well, this function, not f, but f times lambda alpha over m. And it has a period depending on alpha. And well, I must be more precise here because this is tau over m. So I have an error here. It's m alpha over m tau. But as far as the limit is concerned, no problem. This limit at tau tending to 0 exists if and only if. So, and alpha is in the set where the limit exists. The limit at alpha exists if and only if this limit when tau tends to 0 exists, which means that this function f times lambda alpha over m has mean value 0. And what is this? Well, it's a mean value, so it's a finite sum. But here you have the sum over n modulo m alpha. You take a complete system of... Yes, m alpha, sorry, I didn't write it. And maybe I didn't say it. This is the period, I mean, of this new thing. Yeah. And so this new periodic function, you compute its mean value, and you have such an expression, I pi n square alpha over m. So this is called usually a quadratic Gauss sum, and it's a classic topic in number theory. So here we have the setup for the boundary function. It will be defined on that set. So, okay. So we will be interested in this function theta. So that's part of the aim. Understand this function. Maybe we want to understand its values at integers. That's a very special case. If k is an integer belonging to that set, or maybe we're interested in the value at 1 over k for some reason. Let me explain that maybe now. And maybe we will find some modularity. This is a classical topic for Theta series. There will be modularity, and there will be also quantum modularity. So this is the end continuing here. Modularity means you consider, or quantum modularity, you consider the actions of gamma. So action of gamma, that kind of linear fraction, where this A, B, C, D, so it's essentially the same as what? Up to a sign, plus or minus this matrix, this is gamma. So this is supposed to belong to a subgroup of SL2Z. So meaning that these four numbers are integers, the determinant is 1. So this is the modular group and the full modular group here, but maybe we consider a subgroup. And maybe when we let this, we consider all these gammas in this subgroup and we let this act on our function theta or the limit function, maybe something happens. That's the story of modularity. So you must remember that this full modular group is generated by the translation, the unit translation, and the negative inversion. So T of tau is tau plus 1. S of tau is minus 1 over tau. So by the way, maybe here there will be something happening between 1 over k minus k due to the action of S. This is one thing we will get. motivation, I said we want to have a good unifying framework for various phenomena. And this phenomena comes from number theory. Maybe F has interesting arithmetic properties. It also comes from topological quantum field theory. So let me give just an example, a historical example. If you consider period 12 and a function f with, or let me say f is like this and f of n is like that, and the support is only 4 numbers per period, and I choose the value 1 here, -1, -1, 1, so this function is even, 12 periodic, and the values which are not indicated, they are just not in the support, so the value is 0. Yes, that's the Dirichlet, primitive Dirichlet character of modulus 12, yes, indeed. And so in that case, for that particular f, if you choose nu equals 0, you find the famous Dedekind eta function, which is well known to be a modular form of weight 1/2. And if you choose theta, sorry, nu equal 1, then it is sometimes denoted by eta tilde. And there is a paper by Don Zagier in 2001, topology 2001. Zagier is the one who invented quantum modular forms. And well, that was one of his starting points. This strange function eta tilde, topology in, yes, I think it's this one. And by the way, this was worked out in the framework of Resurgence by Costin and Garoufalidis in 2011. They have a paper about this, the resurgence behind that function eta tilde and its quantum modular properties. So we will explain what it means in a moment. So this is just one example. Yes, the title of that article is Resurgence of the Kontsevich-Zagier series. Yeah, there is a question, yeah?
So I'm just confused about it. So here the mean value of, by mean value of f, you just mean the mean over the period, right?
Yes, the mean value is 0, yeah.
So I thought the eta function at 0 has a 1/τ⁴ behavior.
Sorry?
The eta function when tau goes to 0?
Yeah, maybe.
So the limit doesn't quite exist.
Yeah, I mean, maybe there is some, I was a bit simplifying here. Let me remember. Yes, we have to do something when nu is 0, yeah. And when f is even, there is, this is not quite correct. There is a slight twist. Thank you for pointing that out. I mean, it was just, you will see what happens because, I mean, the story is that when f is even and nu is 0, it's, if f of 0 is not 0, well, you should include n equals 0 with weight 1/2. It's like that, it's a recipe. And this has consequences everywhere in the theory. And okay, we will see that, I think, in a moment. So another example, quite important, in which Zagier played a role. I mean, there is this paper by Lawrence and Zagier in 1999. So this is related with topological quantum field theory, quantum invariance for 3 manifolds. So I won't enter into the details for that. Anyway, I wouldn't be competent. Let me put it here. Well, let me say it like this. We were quite influenced in our analysis by a paper by Sergei Gukov, Marcos Marinho, and Pavel Putrov. So it's a preprint in 2016. And in fact, they were refining and they were investigating something which goes back to Lawrence and Zagier. I think it's 99. And very recently, there was a paper by Anderson and Mistergaard published in Journal of London Mathematical Society this year. And there is Resurgence in the title, so it's easy to find. And so the leading example for that particular leading example is, so it looks strange. I mean, period is 60. Well, 60 is twice P1, P2, P3, where P1, P2, P3 are 2, 3, 5. And indeed, this corresponds to the so-called Poincaré homology sphere, which is sometimes denoted sigma 235. So this is a three-manifold. Closed manifold in dimension 3. And there is this business of quantum invariance, which is a fascinating story, which has developed in the past decades. And so for that case, we are dealing with a very specific function f, which is odd, 60 periodic. And we are interested in theta of tau with nu equals 0, f 60. Yeah. And what can I say about this example? Well, Anderson and Mistergaard have generalized that to not only Poincaré homology sphere. They consider any P1, P2, P3 pairwise co-prime, and this defines the so-called Briscoe sphere. But you can even have more numbers, and then it starts being more complicated. You can have R numbers, R is at least 3, pairwise co-prime, and then you have what is called a Seifert fibered 3 manifold. But the point is that all these 3 manifolds have the same homology type, like the sphere. So the story of the quantum invariance is to distinguish between them. They have the same homology, but can we find invariance to detect the difference between them at topological level? So the point is that for all these examples, you have the same story. You have a partial theta series with nu equals 0. And in this case, the period is twice P1, P2, P3. And here, you have a superposition of finitely many partial theta series with various values of nu. So it's more complicated. You have a superposition of nu equals 0, nu equals 1 until r minus 3, I guess. Something like that. So it's more complicated, but so our analysis in principle is relevant for that. At least Anderson and Mistergaard think so. It's funny because Anderson, Marinho, and also Gukov and myself, we participate to an ERC project, which is called Renew Quantum. Renew Quantum. So Anderson is one of the principal investigators. Kontsevich is another one. So we are all in this. So we will see soon and try to do good resurgence and try to pursue the analysis. So let me tell you at least the beginning of the story. Yeah, so I'm sorry I cannot tell much about Chern-Simons theory with SU2 gauge group, but maybe I should say one thing. What is interesting, what Anderson have proved in quite a general context, I mean, for these manifolds, is that, I mean, building on the works of previous people, like Gukov in particular, and there is a recent paper by Gukov and Manolescu, I mean, a lot of papers, activity in that domain. What happens here is that this function here, or in general that one, or the superposition, blah, blah, blah. So this particular partial theta series is essentially the GPPV invariant, the Gukov, Pei, Putrov, Vafa invariant. So the partial theta series, when you view it as a Q series, it has integer coefficients. So it's kind of a generating series for interesting numbers. So this is the function of tau that we have. And so this is the function theta of tau. And they were interested in what happens when theta tends to, when tau tends to 1 over k. And then there is a connection with the WRT invariant at level k. Witten, Reshetkin, Turayev invariant at level k. So this is the kind of phenomenon we want to understand. And I forgot to say, but in fact, yes, let me show you something very easy with the function theta of tau. Let me introduce the
theta function has, sorry. The theta function, as you defined it, has some periodicity with 1 or m or something like that.
2m.
2m, right?
Yes.
So if there's any kind of modularity, it's kind of funny that in 1 over 2m there is a period.
Indeed. Well, and look at this. I mean, what I'm going to say is slightly related. Look at this. The residue, I mean, the class modulo z, and this is a rational number, n squared over 2m minus, and I take its equivalent class in Q modulo z, okay? And assume the support of F happens to be contained in one fiber of that map. Imagine for all the elements n of the support of F, you remember we have sum of f of n, blah, 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 and well, f of n, and nu f of n, and it's exponential I pi n squared tau over m. Imagine all these n, when f of n is non-zero, give the same zeta modulo z. What is the consequence? It's easy to check that. Then, when you compute theta of tau minus k, something will happen because it's always the same modulo z, and you take the exponential. So you get exponential 2 pi I k zeta theta of tau. Very easy property. I mean, I'm saying that for fixed tau, this is a periodic function of k of period 2m. And here I'm saying, well, in fact, there is only one Fourier mode for this particular periodic function. And when you go to the limit, when tau tends to 0, you find that, okay, the boundary function of at minus k will be just given by, has only one Fourier mode. And this Fourier number, zeta, which appears here, well, this is the first theorem in their paper. The Chern-Simons values in their problem happen to be exactly those numbers zeta. I mean, so there is a connection. Well, I don't want to enter into the detail. I must go forward, yeah. But well, the Chern-Simons values are connected with the possible values of zeta. So this is why, remember, we are interested in the boundary function, maybe the values at integers, maybe the values at 1 over k. So value at 1 over k, this will tell you something about WRT. the value at k and its Fourier numbers, that will have a relation with the possible Chern-Simons, with the range of the Chern-Simons integral in that problem. I'm sorry for the, if you don't know these names, well, I recommend reading Anderson Westergaard's paper. Good. So what do we do now? How do we see resurgence? So resurgence, it's about the use of the Laplace transform. Let's say it simply like that. It's a particular way of using the Laplace transform. And so let's go to our first result. First result. So theorem 1. Well, in fact, it's implicit in the GMP preprint. And also in Anderson Westergaard. And in fact, I could trace it back to a paper by Flageolet and Noy in FPSAC 2000. And probably there are earlier references, you will see. Consider f of t, the generating function for with exponentials. You see, let me call this an. So this is my function theta of tau. And I consider this generating function here, no n square, and it's n. And if an is periodic, then certainly it's interesting to compute that function, and it's manageable. So, but well, here, because f of n is bounded, so this function is holomorphic and even bounded on, let's say, real part of t at least c, and this c is arbitrarily small positive number. So this is a function which is in the problem. Then consider now f hat of psi to be 1 over square root of pi, psi to the minus 1/2, f of c psi to the 1/2, where c is a very concrete number, square root of 4 pi over m, exponential I pi over 4, exponential I pi over 4. So let's have a look at what happens in the t plane and in the psi plane. So in the t plane, we have essentially it's holomorphic for real part of t positive and bounded as soon as you move a little bit the vertical line. So it's holomorphic in this right half plane in the t variable. But here we must divide by c and square. So when we divide by c, we rotate this by pi over 4. And then when we square, what happens in the psi variable is this. So we have rotated by, and then we square. So pi over 4 becomes pi over 2. And this is minus 3 pi over 4. It becomes minus 3 pi over 2. So this function here in the psi variable is holomorphic for minus 3 pi over 2 less than argument of psi less than pi over 2. And theta is nothing but 1/2 tau to the minus 1/2 integral over gamma epsilon of exponential minus psi over tau phi hat. So this is the Laplace kernel when you think that the variable is 1 over tau. So we will have Laplace transforms evaluated at 1 over tau. For the moment, it's not exactly a Laplace transform. It's slightly modified because this contour gamma epsilon, what is it? It's something like this. You come from minus 3 pi over 2 plus epsilon epsilon is arbitrarily small, positive. You go toward the origin, but you circumvent the origin, and you go back to infinity in direction pi/2 minus epsilon. So this is my path, gamma epsilon, my contour. So this is a Laplace-like integral on the contour of phi hat up to the tauton minus 1/2. So this is the first result. Let me show the proof. It's very short using Borel-Laplace. I don't want to be too technical, but I want to show you how it works. I mean, it's very concrete and very elementary. It's complex analysis. So what you must know is that when you have a convergent series, it is equal to the Laplace transform of its Borel transform. So let me consider exponential sigma squared tau. And I expand it. So this is a convergent series with the factorials. And for some reason, I have multiplied by tau to the 1/2. So this is a convergent series with this slight singularity. So it is the Laplace transform of its Borel transform in any direction. What is the Borel transform of that guy? Well, you must learn the recipe. So you take the coefficients and you divide by a sum gamma. So it's the gamma of that exponent. And then you end up with psi power, the same power minus 1. That's the recipe. Just a simple recipe. If you start with convergent, you divide by the factorials. Gamma is essentially factorial. So it's even more convergent. So now it's convergent everywhere. Well, it was convergent everywhere already. Well, and there is this mild singularity at the origin. But I told you it is the Laplace transform of its Borel transform. So the Borel transform, you see, the singularity at the origin is integrable. So here, maybe you can guess why I have divided by, why I have inserted this tau to the 1/2 is to make my life simpler. I mean, this coefficient, this denominator is nothing but factorial 2p with square root of pi divided by 2 to the 2p. Hence, we end up with this beautiful formula. Pi to the minus 1/2 coming from the denominator, psi to the minus 1/2 coming from here, and then it's essentially the exponential series. 2 sigma psi to the 1/2 power 2p divided by factorial 2p. So it's the even part. And we select even indices in the exponential series. So let me say this is the odd part because of the, I mean, even powers of psi to the 1/2, even powers, but there is one odd power here. So it's the odd part of something, let me call it psi of psi to the 1/2. It's just the exponential. Pi minus 1/2, psi minus 1/2, exponential minus 2 sigma psi to the 1/2. And I told you a convergent series is equal to the Laplace transform in any direction of its Borel transform. The Borel transform is this odd part. I mean, with obvious conventions for the branches when we see power 1/2. So for any theta, For instance, you can take theta to be pi over 2 plus or minus epsilon. Any theta is good. So let me end the proof here. Let me end the proof here. Well, what will happen when we consider L pi over 2 plus epsilon of that piece? And psi, you see what psi is. As a function of its argument, it's just an exponential. So when you change psi, you change the branch, it's equivalent to changing the direction to from pi over 2, you go to minus 3 pi over 2 plus epsilon. And you take the other branch, okay? So the upshot is tau to the 1/2 exponential sigma square of tau is 1/2 pi inverse pi minus 1/2. And then you have minus the Laplace integral in this direction. Plus the Laplace integral in the direction pi over 2 minus epsilon of the same thing, which is this psi to the side 1/2. So, well, let me write the Laplace kernel. And we must not forget this sign. So let me repeat, exponential minus 2 sigma psi 1/2 d psi. And of course, now I'm integrating exactly on the ray and here back, and I have no problem at the origin. But in a minute, I will have a problem. So it's safer to replace that by the same thing over gamma epsilon. So now I introduce gamma epsilon. And now I say this is for every sigma. Apply it with sigma square. So this sigma square, suppose it is I pi over m n square. And then correspondingly, 2 sigma will be, well, this C here. So this strange C appears here. And the point is that here you have n square in the partial theta series, and here you have n in the integrand for the Laplace-like transform. So we have gone from a sum involving n square to a Laplace-like integral involving phi hats of psi, which is the generating series with the n's evaluated at c times psi to the 1/2. So this is the Borel-Laplace proof of that identity, which was already used by the other guys in this story. Good. Now, what is the story now? In our problem, the sequence an, well, is n power nu f of n. So what will be the function f of t in our problem? It will be a very concrete meromorphic function. So with a view to applying our formula, this formula, let us have a look at this f of t. So clearly, this is minus d over dt nu times of f0 of t. And f0 of t, what is it? Well, it involves f which is periodic, so you can prove there is a very simple formula, a rational function of exponential minus t. So here we take L between 1 and m. So when you use that, you see that you differentiate. So potentially there is a pole at the origin. And what is the residuum of, you see this is as a function of t. This is entire, and I divide by this, which has poles on the imaginary axis and at 0. What is the residuum at 0? It depends on the value at t equals 0. It depends on the mean value of f. So f of, and then you differentiate t nu times, and you end up with this. So there is this potentially singular term, unless mean value is 0. And then the rest. Well, the rest, let me split it into two parts, f plus and f minus. And f plus is the even part in t. Any function, I can split it into odd and even. And what is the even part? Well, let me write it, because I want to go to the variable psi. I must do this change of variable. T will become c times psi to the 1/2. So let me say, an even function, I can write it like this, phi plus. And an odd function, I can write it like that, phi minus of t square over c square with t over c in front. And well, to be very precise, I put pi to the 1/2. So now I can compute these two functions, phi plus and phi minus. They are regular at the origin. These are honest Taylor expansions at the origin. And when you put them together, I mean, when you compute the sum, they have a meromorphic continuation in the psi variable. But in the psi variable, we are living now on the Riemann surface of the square root of psi. But apart from that, and where are the poles, by the way? The poles, they were at Tn is 2 pi I n over m. But when you do the change of variable, now the poles in the psi variable, they are located at I pi n square over m. This was the purpose of my initial convention for the scaling of the tau variable. I wanted to have the poles in the psi variable located exactly at the Fourier numbers of my initial Q series. Okay, what do we get from here, from this? So you remember we are integrating over this contour because we have detached the contour from the origin, and that was a good idea because you see that in general there is a singularity at the origin because t becomes psi, etc. And it's not difficult to compute. So yes, let me write at least once the formula for phi. So we are supposed to compute the Laplace-like transform of phi hat, which has been obtained in the form. So there is a coefficient times mean value of f. So in the variable psi, we get this minus mu over 2 minus 1. And then this contributes psi to the minus 1/2 phi hat plus. And this other piece contributes phi hat minus. And now here is the beautiful thing. what is the landscape in the psi variable. So psi will be our Borel variable. What does it look like? So we have the imaginary axis. This is the psi plane. We have these poles located here. And we are supposed to integrate over gamma, which is like this. And yes, because there is here, usually there is a pole, well, not exactly a pole, I mean, but a negative power. Well, you contribute separately, you can compute separately the contribution of that guy. This is Borel-Laplace dictionary. What is you compute and you find this. Let me write it clearly. Yes. So putting this together with the first theorem, we get theta equals, so a coefficient, let me skip it, mean value of f times, let me put tau over I. I like tau over I because tau is in the upper half plane. I rotate and then I take the principal branch for the square root. So this is the contribution of the first term. And then there is a theta plus coming from this term, and there is a theta minus coming from that term. And the beauty, so you see, we have isolated the singular part. And now for the rest, for this part and that part, we can use really the usual Laplace integral because there is no singularity at the region. So we can close the contour, we can push it through the origin. What does it give you?
Plus or minus, or is the Laplace?
Yes, exactly. Theta plus is exactly. Theta plus is, let me write it like that.
Excuse me?
It comes from that guy. Okay. Yes?
Yeah, that was my question. So phi plus and phi minus, you are referring to the positive and negative half planes, right?
So phi plus.
Pi by 2 and minus 3 pi by 2, right? Phi plus.
Say it again more slowly because the sound is poor.
You're referring to phi plus at pi by 2, right? That branch of the gamma contour?
What I'm doing is that I have computed f, I have deduced phi hat in this form, and it has 3 pieces. We have taken care of the first piece, and now we are dealing with the 2 other pieces. So what is the second piece? Let me write the formula.
Yeah.
So even and odd part of f, sorry, I didn't get it, the question. I have this very concrete meromorphic function of t. It has a Laurent expansion at the origin, and I separate, so I have this for the polar part, and I have the even part and the odd part, simply this. So you have f plus of t is up a part. If you neglect that, it's f of t plus f of minus t divided by 2. This is why it is still meromorphic, by the way. Now, here is the beautiful thing. Theta plus is 1/2 tau minus 1/2 integral over gamma Laplace kernel, and there is this psi to the minus 1/2 phi plus. And gamma, you remember, gamma it starts from 3 pi over 2 minus 3 pi over 2 plus epsilon, and it ends at pi over 2 minus epsilon. But well, what about using the other branch? The other branch has pi over 2 plus epsilon. Well, if you do that, instead of this, I want to use the other one. But, well, phi plus is regular, but there is the change of branch. So I get a minus from here. So now I can use, and here is the result, 1/2 tau to the 1 minus 1/2. And now this is the usual Laplace transform in direction pi over 2 plus epsilon plus Laplace transform pi over 2 minus epsilon of the same thing, psi to the minus 1/2 phi hat plus. So I'm using systematically this notation for the Laplace transform. Okay, so you understand, I was supposed to integrate like that, but I changed branch, so I changed direction because of the change of branch here. But in the case of theta minus, it's different. In the case of theta minus, when you play the same game, you get no sign minus. So you have this one, yes, and you have minus this one, because it's not the same parity. So let me write it like this. So finally, we got our Laplace transform. We got 4 of them. We have 4 Laplace transforms which appear naturally in the problem. And well, immediately I can tell you that this guy, difference of Laplace transforms along this contour of something which is regular here, well, it's an integral over a contour that you can push upwards, you can raise it. So it's exponentially small with respect to tau going to 0. Because the point is that any Laplace transform, you must remember 3 things about Laplace transforms. First thing, once it is written like that, it has an asymptotic expansion, which is given by the term-wise Laplace transform of the Taylor series. So the Taylor series of phi hat will give you a sum of monomials, and you get an asymptotic expansion, which is, what is it? If phi hat is regular, it's something like this. Tau to the n plus 1, something like this. No factorials. Usually it's divergent. If phi hat has a finite radius of convergence. So Laplace transform implies there is an asymptotic expansion which may very well be divergent, but always 1 Gevrey, etc. Asymptotic behavior under control. But that's only one thing. Another thing is the domain of definition, domain of analyticity in which this asymptotic property holds. Well, it's in our situation, you can vary the direction theta. So each time you vary the direction, you increase the domain. So the domain is quite large. That's a piece of information you should never forget. And third thing you have to remember, asymptotic behavior, domain which is large if you can vary the direction. And third thing, if there are singularities in the psi plane, you would like to inquire about their contribution to the difference. I mean, because I said, when there is no singularity, you can vary the direction and you enlarge the domain. When there is a singularity, then there is a jump. There is a difference between these 2 Laplace transforms. So the third thing is you'd better compute this difference if possible. And you will find probably interesting things. That's the 3 things you must remember. That's our message. Maybe I should conclude in 5 minutes. I will try with the alien derivatives. So now you understand why this is exponentially small. This is the difference of 2 functions which have the same asymptotic expansion. Okay, whereas this one, it's the average of two Laplace transforms. So it's the average of two functions with the same asymptotic expansion. By the way, this average must be considered as another canonical Borel-Laplace sum. So when I say Borel-Laplace sum in a direction theta, well, this is Laplace of Borel. And in this context, so let me call this the plus direction and this the minus direction. So here we have, for instance, this guy here. So let me call it little phi hat plus of psi. It has a Puiseux expansion at the origin, which gives rise to a divergent asymptotic series. And then you multiply by tau to the minus 1/2. So in this problem, you have, so you have 1/2 tau to the minus 1/2. This is S plus S minus of the phi tilde, and phi tilde plus would be the inverse Borel transform of the Puiseux expansion. So these are two canonical sums, S plus and S minus, but the average is a third canonical one, which goes under the name median summation. So half the average is the median summation. It looks a bit simple, but it's not that simple in the general context. Ekal has defined the median summation in a wider context. Here, it boils down to a simple average because in the background, we have something meromorphic, single-valued. Meromorphic function doesn't matter how you are going around the singularities. In general, when you are dealing with resurgent functions in the Borel plane, you have multi-valuedness. And so it's not that direct to define the median summation along a singular direction. So, this is the median summation S direction pi over 2. Yes, this is the notation. So now, I'm running out of time, I'm sorry. Let me tell you the interesting phenomenon which appears now and which gives rise to modularity or quantum modularity in our paper. It is the following. Yes, it is the following. When you are following Ekal theory of resurgence, you encode the singularities through alien derivatives. And I told you it's good, and the contribution of the singularities is given by a sum of the Laplace transform of the singularities. So we inquire then on the singularities of that part, which is here, phi plus hat, and the singularities of that part. Well, let me write the formula for nu equals 0. Delta psi n phi n plus, phi tilde. Phi tilde means inverse Borel transform. This is just twice exponential I pi over 4. The discrete Fourier transform of f. So we have f periodic function on z. It has a discrete Fourier transform, like the usual Fourier transform, but variable is integer. And well, not f itself, the odd part of f, evaluated at n. So this is a number. So what is the meaning of that identity? This number equal to the alien derivative, well, it's a systematic way of encoding singularities. When you say, when we see 1 for the alien derivative, this corresponds to a pole with residue 1 over 2 pi I at psi n. So this operator is a linear operator. If you detect a simple pole, you put a constant. And so this is, the residuum is 2 pi I times this. And you have the same with the other part. When you compute the alien derivative of that guy, so again, I'm using the inverse Borel transform, so I get a constant, and it's similar formula with the even part of the DFT, which is the DFT of the even part, by the way. And when u is 1, well, the same is, well, same coefficient with an I. And you have n times f hat even. Now you exchange. And here you have twice I exponential 3i pi over 4, 3i pi over 4. And you have n times f hat dft of the odd part. And I forget tau inverse. So when you see tau inverse, it means derivative of a simple pole. It's a double pole. So which means that we have an interesting phenomenon here, because this delta xi n will come with an exponential attached to it, because we are, when you do what we are doing here is computing a difference. So each singularity contributes with a coefficient depending on the strength of the pole and an exponential, because the Laplace kernel gives this remnant exponential minus xi n over tau. So this is the object you want to compute. This is called the directional alien derivative in Eka's papers in direction pi over 2. So the phenomenon that we discover here is that, so let me wrap up everything. The directional alien derivative of theta tilde, the formal series which will appear eventually due to theta plus. Remember, there is a singular term. Well, let's suppose the mean value is 0, it's not here. And then there is theta plus, well, there is the tau to the minus 1/2. So it's this theta tilde is tau to the minus 1/2 times phi plus tilde. And I'm saying that if we were interested, I mean, we are supposed to compute the average, but suppose for a minute we compute the difference instead of the average. Why not? We will find this twice tau over I minus 1/2 due to the correction here, tau to the 1/2 in the front. And then this will be a new theta function evaluated at minus 1 over tau, because these xi and a are exactly the ones. So, but except that it's not f if it is rather f hat odd, dft of the odd part. And similarly for the other part, you know, there is another part. If you are interested in this guy, let me say tau to minus 1/2 phi tilde phi tilde over 2. And this is something we were, I mean, this was a funny idea. I mean, I'm supposed to compute the average and I compute the difference. But this is required. I mean, theta minus is the difference. So I need to compute this Stokes phenomenon, this sum of contribution of singularity. And what do I find? I find again a theta function, but evaluated at minus 1 over tau using the even part of the DFT. And so you see here the modularity starting here. I mean, the relation between tau and minus 1 over tau, except that this is f and this is f hat, not the same. And there is the weight 1/2 in the case of nu equals 0. And if you do with nu equal 1, the weight will be minus 3/2. I mean, the weight will be 3/2. So when you look at the paper, you will see that this has nice implications now. Imagine you start with f even and nu equal to 0. Then f even nu equals 0, there is no theta plus, only the theta minus, and you compute the theta minus, it's this, it's a new theta function at -1/tau, but for the DFT of f. F is even and you compute its DFT, which means that if you consider the vector valued function in which you consider simultaneously the partial theta series for f and the partial theta series for f hat, now you have a standard modular transformation for transformation rule. Vice versa, if nu is 0, let's think of Seifert fiber manifold with 3 exceptional fibers. Nu is 0, but f is odd. So this is the strange case. F is odd. In that case, there is no theta minus. This exponentially small term is absent. So really the GPPV invariant in that case is nothing but the median summation of something. And if instead of computing this median summation, you compute the difference, then you have this phenomenon. Again, this f is odd now, f is odd. And we observe, oh, this is a theta function at -1/tau for f hat. So again, if you do the vector valued construction, so what does it mean? Let me conclude on that. I'm saying that my theta function is, in that case, suppose the mean value is 0, suppose f is odd. So nu is 0, f is odd, and the mean value is then 0. So in that case, I just have theta plus. I just have the median summation, which is Laplace plus Laplace minus over 2 of one thing, which is called, or let me say S plus, S minus summations of the same divergent series, which comes from our computation. And I computed the difference, and it was interesting. Well, let me say that this is S plus theta tilde minus half the difference, minus half the difference, S plus minus S minus. Or if you prefer, it's S minus plus half the difference. So I'm saying that there will be a modularity phenomenon appearing here. So if I put it on the other side, I'm saying theta of tau plus the other partial theta series at -1/tau. This is not exactly 0 as it should be, but it is S plus. And S plus, this is one of the canonical summation, which has a very large domain of analyticity because you can move theta plus in the direction in the psi plane, which means that in the tau variable now, we are no longer prisoner of the upper half plane. I mean, if my direction is very close to the imaginary axis, I have access to the upper half plane. But if I move my direction this way, I'm enlarging the domain of analyticity like that. In fact, until here, I mean, the point is I can cross the real axis. I can cross the real axis. So there is this unexpected property, the modular obstruction, theta of tau plus the thing to which it is, or minus the thing to which it's not equal. Well, but when you do this difference, you get this modular obstruction, which has a nice analytic continuation through the real axis. And by the way, if you evaluate it at 1/k, and k tends to infinity, well, it's summation of the usual series. So again, it's always the same asymptotic expansion when k tends to infinity. Well, I'm very sorry if the end of the talk is probably a bit too fast. Have a look at the paper if you are interested, and I thank you very much for your attention.
Let's thank David. Okay, time for questions. Online AV team, can you enable the online participants to unmute themselves? Yeah. So online participants, please just unmute yourselves and ask questions or raise your hand if you're not able to unmute yourself. Questions?
questions, but they're not relevant to these calculations. So can you talk about differential equations in this alien derivatives? And do these thetas somehow satisfy some differential equations in those alien derivatives?
So when you say differentials, you mean derivatives with respect to tau?
No, what I mean is this.
Delta, the alien derivatives.
Delta pi by 2, can you apply it many
times? Yeah, in this case, because the problem is so simple, because it's meromorphic in appropriate variable, when you apply it in second time, you get 0. You see, the alien derivative of our series are constants. So the alien derivatives of constants are just 0. So this is why in this problem, if you remember the talk about alien derivatives, the delta and the delta plus coincide. So it's a situation which is very simple, and this is why the Stokes phenomenon is so easy to compute in this situation. So in this particular situation, it boils down to almost nothing. But the flexibility that gives alien calculus is that, for instance, when you go to the Q variable, you can rephrase everything in the Q variable, and maybe instead of an asymptotic expansion when tau tends to 0, you prefer an asymptotic expansion in powers of Q minus 1. So this is a change of variable, an analytic change of variable within a resurgent series. It's perfectly handled. And then you can compute the alien derivative of the series in Q minus 1 using the alien chain rule. I mean, the alien derivative of a composition, because you have change variables from tau to Q minus 1. So you have this flexibility. This is why we think it's good to take this effort to rephrase everything in Ekal's resurgence language.
Other questions? Online audience?
Just to verify, this S plus, this lack of modularity, that's exponentially suppressed in tau?
Yes.
Yeah.
Yes, indeed.
Mm-hmm.
The difference of two summations, S plus minus S minus, is always exponentially small. But the modular obstruction is this guy. So, I mean, this exponentially small quantity will be the value of the partial theta series at minus 1 over tau. The S plus is not exponentially small. It has an asymptotic expansion, which is containing powers of tau. Containing powers of tau, yes.
Sorry, it has an asymptotic expansion near tau equal to 0, that's what you're saying,
yeah.
With positive powers of tau.
This is why for instance, you may evaluate it at 1 over k and let k tend to infinity. And you see that, and you have this funny phenomenon that, for instance, theta at k, let's say, theta at 1 over k, theta at 1 over k, it will come from here. So you can write it as, so there is some coefficient here, I don't remember, k, and there is theta of k, of minus k, plus v or minus, I don't know, s plus the summation at 1 over k. So this has an asymptotic expansion, negative powers of k, which gives you the asymptotic behavior up to this oscillatory part. This is a periodic function of k, which maybe has only one Fourier mode in the relevant problems, by the way. Well, except that this is f and this is f hat. So you have to compute f hat, but the primitive Dirichlet characters, when they are real, they are eigenvectors of the DFT. And in the case of fiber-Seifert manifolds, you have interesting relations between f and f hat. Well, it's a long story then. It's another paper that we must prepare.
Other questions? If there are no further questions, let's thank David again for a very nice talk.